I'd like to thank the organizers for the invitation to speak, and also to thank Mike for providing the great excuse for this conference. I actually haven't known Mike for very many years. I only met him maybe 5 or maybe 6 years ago now. But it's been a great time since then. I've learned lots of interesting maths and been to some fun places, and I can attest to Mike's enormous energy, even at the age of 60, both doing mathematics and some other things. That's Mike at a pre-dawn start on a climb up Mount Whitney. We had many hours of service that day. But of course, he did just fine. The talk today is about four-manifold invariance from Khovanov Homology. And this is all going to be joint work. I guess I can stand in front. This is joint work with Chris Douglas and Kevin Walker. And what I'm going to do is define an invariant for that A of smooth four-manifolds, which takes value, which gives you a doubly graded vector space for a smooth four-manifold. If this manifold has boundary, you can specify a link in the boundary, and the invariant also depends on that. And it's a generalization of Khovanov Homology, in the sense that you stick in the four-ball and a link in the boundary of that four-ball. You just get the usual old-fashioned Khovanov Homology of that link. Now, the way this talk is going to be organized is, first of all, I'm going to describe the general framework we're using, which I guess, in some respects, Peter's talk this morning laid a lot of the groundwork. But that part will sort of be divided into two pieces. First of all, I'll talk about some general nonsense about higher categories and TQFTs. And in the second half of the first section, I'll make very explicit exactly what we need in the higher category world, and describe exactly the algebraic gadget that we're using here in build format for invariants. The middle part of the talk will be all about Khovanov Homology. We'll have to check a few details and learn a few extra things about Khovanov Homology, which maybe we didn't previously know. And then at the end, I'll talk about, well, the prospects for doing calculations with Okay, so what's the framework that we're working with today? First of all, there are no new ingredients in this. There are no differential equations. We're not trying to categorize all quantum group theory. We're just taking what we already know about Khovanov Homology, and has been around since the early days of Khovanov Homology, this combinatorial description of a non-invariant. And we'll realize that with just a little bit of extra work, we can build a four category. And using that four category, we can then follow a very standard recipe for building invariants of manifolds. So I just want to say a little bit about what that recipe is and which aspects of the usual recipe we're going to use today. So first of all, there's this general idea that an n category, maybe a pivotal n category, you have to have some notion of duality. An n category gives an n plus epsilon dimensional TQFT. Now, what do I mean by n plus epsilon? Well, it should associate vector spaces to n manifolds, but it doesn't necessarily associate anything to an arbitrary n plus 1 manifold. It just gives you linear maps for mapping cylinders. Now, one place you can go read for a description of how to build TQFTs from n categories is our discussion of disk-like n categories in our paper on the blob complex, but there are other ways if you prefer to think about this. Now, you can get a little bit more. If the n category satisfies certain extra conditions, which I'm not going to attempt to discuss at all here today because we're going to mostly ignore them, but there are these extra sort of finiteness conditions, then you can get a proper n plus 1 dimensional TQFT. Not only do you get vector spaces for n manifolds, you get linear maps for n plus 1, for arbitrary n plus 1 manifolds. And the idea that the words that you should have in mind for these two things are that to an n manifold we associate some scheme module, and we calculate some state sum or partition function associated with an n plus 1 manifold to get these linear maps. Now, this recipe is very general and encompasses lots of wonderful examples. And I want to sort of show you in these examples, the difference between the n plus epsilon dimensional TQFTs and the n plus 1 dimensional TQFTs. If we just have a tensor category with some duals, we can build vector spaces for surfaces. Essentially, in Peter's description of string diagrams, you draw the string diagrams on the surface, modulo relations that hold in disks. And this is the sort of classical notion of a scheme module. It gives you a vector space for a surface. If you add some extra conditions to your tensor category, in this case, a fusion category is a good thing to aim for, you also get maps for algebraic manifolds. Now, in the wooden relations you can derive setup, I'm going to say this a little bit funny and then explain why it seems a little funny. For a braided tensor category, well, a braided tensor category is just a special type of tree category. And actually, if you don't know and love that fact, the braided tensor category is just a special type of tree category, then probably you should interrupt me right now and say, stop, explain it, because otherwise this whole conference is pointless if you don't know things like that.
Stop, explain it.
Stop, explain it. Okay, so, well, maybe I'll just explain the first bit, an easier version. I mean, a tensor category is just a special sort of two category. Okay? If you have a tensor category and you have objects and morphisms, you can bump this up and build a two category. So now we're going to have objects, one morphisms, and two morphisms. Okay? So what are we going to do? The only object in this new two category, there's only going to be one. We don't even need to give it a name. Maybe we call it turtle. Then we take all of the objects in our original category and call them one morphisms for the new thing we're building. And we take all of the morphisms from the tensor category and call those two morphisms in the two category we're building. Okay? Now remember from Peter's description in the two category, there's this horizontal composition and a vertical composition. One of these directions, say the vertical composition in Peter's language, should just be, well, what are we doing? We're vertically composing two morphisms. Those were one morphisms in the old picture, so we just compose them the usual way. Then we need to describe what horizontal composition is, and that's just the tensor product back in the old language. Similarly, one step further along, a braided tensor category, you can take your braided tensor category and move everything up two levels. You have trivial stuff for the objects, trivial stuff for the one morphisms, and your old objects and morphisms become the new two and three morphisms. And thinking about horizontal and vertical and other direction compositions, you can get all the structure of the braided tensor category. Oh. Braided tensor categories are three categories. So this general machinery says at least we get vector spaces for three manifolds. If you satisfy some finiteness condition, you also get maps for four manifolds. But this is not at all the usual way to talk about wooden measures you can derive theory. We're used to thinking of those invariants as being one dimension down. Vector spaces for two manifolds and maps for three manifolds. And the point here is that if you start with the modular tensor category, the representation theory of a quantum group for the root of unity semi-simplified, then these invariants that we build from this recipe only depend weakly on the interiors of these 3 and 4 manifolds. So if you want to recover the usual story from this recipe, you should think of these invariants as being associated to the boundaries. They don't really care about what you put in the interior. So one way to say this very explicitly, if you want the Taranto vector space for a surface in the usual language, well, what do you do to get it out of this picture? You look at the solid handle body. So, wooden measures of Taranto theory. So from the vector space for WRT theory, you pick the solid handle body whose boundary is the surface that you're interested in. And now you just look at ribbon diagrams in the interior of the solid handle body, maybe with some coupons, depending on what sort of braided tensor category you're working with. The morphisms can label little coupons inside the solid handle body. And we take these ribbon diagrams, modular local relations, and that's exactly the vector space that you meant to associate to a surface. Okay, so that's all very well, but to the point for the rest of today, I would argue that this simplification is maybe a little bit misleading. And if we want to work with Khovanov homology, we should not do this. So one way to think about this is that Khovanov homology so far shows no sign of special behavior roots of unity, like happens for quantum groups. And so maybe it's best to forget everything that we learned about quantum groups and roots of unity and the special things that happen for TQFTs for quantum groups and roots of unity. Let's just remember that a quantum group gives us a 3 category, and so it gives us some 3 plus epsilon dimensional TQFT. Well, when we have Khovanov homology, instead of the quantum group story, we'll be able to build a 4 category rather than a 3 category, and hence we'll get some 4 plus epsilon dimensional TQFT. And that's all we're aiming for today. We want to produce vector spaces for 4 manifolds, but since we don't have the full 4 plus 1 structure, we're not going to associate anything to 5 manifolds. We just want the vector space invariance. Okay, that was a whole lot of stuff about higher categories and low-dimensional T-curve-Ts, but you can forget it all now, okay? That was just for experts. Let's get completely explicit and talk about the specific algebraic gadgets that we need to use Khovanov homology. So first of all, let me define for you a lasagna diagram. So first of all, there's a big four-ball called B0. And inside that, there's a collection of disjoint embedded four-balls. So this picture just has two of them, B1 and B2. We also want a surface in the complementary region between the outer ball and the little balls, which are called sigma. And we want it to meet all the boundaries nicely, transversely. So in particular, if we call the boundary of BI SI, when we intersect the surface with that boundary, we'll get some length. Okay? So each of the spheres on the interior balls and on the outside ball has some length, and there's a surface in the complementary region that meets all those things. Okay. That's a lasagna diagram. What then is a lasagna algebra? Well, a lasagna algebra A consists of, for each embedded link in a three-sphere, some vector space. For each lasagna diagram, a linear map from the tensor products of the vector spaces associated to the inner spheres to the vector space associated to the link in the outer sphere. Now, we want some conditions on these maps that the lasagna algebra associates. First of all, the map can only depend on the lasagna diagram after isotopy. You can move the surface sigma around, and you shouldn't change the map at all. And secondly, the lasagna diagrams have a natural gluing operation. Say I have some big lasagna diagram, and one of the small balls has some particular link on its boundary. Well, I can take another lasagna diagram that has that same link as its outer boundary, and I can paste the big lasagna diagram, I can paste the small lasagna diagram into one of the holes of the big lasagna diagram, and get another lasagna diagram. Okay? So the linear maps that we associate with these should be compatible with gluing lasagna diagrams, in the sense that you should be able to sort of apply your lasagna map to some of the tensor factors corresponding to the inner ball, and then apply the outer lasagna diagram to the remaining tensor factors. Okay. That's a lasagna algebra. What can you do with lasagna algebras? Well, completely trivially, you get an invariant of four manifolds. So I'm just going to define this vector space now associated to a four manifold. This vector space is a linear span of labeled lasagna diagrams in the four manifold, modulo applying lasagna maps and balls. So forget the relations for a moment. What are labeled lasagna diagrams? I just draw one of these same sorts of pictures in my four manifold W. I cut out some interior balls, I put some surface in the complementary region, and the surface meets everything in some link. Some links in three spheres on the inside, and some link in an arbitrary free manifold bounding this four manifold on the outside. Okay? Now what does labeled mean? Well, in each inner ball, I put an element of the vector space that the lasagna algebra associates to that sphere. Okay? That's a lasagna diagram. And I guess I implicitly linearize. So like, if I replace one of my inner labels with twice its value, that's the same as just multiplying the whole label lasagna diagram, basically. Okay. So what are the local relations that we then impose on this huge vector space spanned by these things? Well, what we can do is, inside of this lasagna diagram, imagine there's some slightly bigger ball embedded that completely encloses some subset of the balls we cut out. Okay? Then what we should be able to do is cut out everything inside that medium-sized ball and replace everything in that with the image of that lasagna diagram acting on the elements inside the inner balls. Okay? So I want you to imagine this identity over here happening somewhere inside the interior of this four manifold. You see some stuff with labels on some inner balls, and you just chop all that out and apply it, take the lasagna algebra gives you a map associated with this diagram, and you just apply it to the labels X and Y. And now you have a bigger ball with that label. Okay, so that maybe sounds silly and too easy, but it's certainly a four manifold invariant. We didn't make any choices along the way. There's nothing to check about the invariant. And it's the right thing to do. This is exactly how you produce the scheme modules and derive your own Wood-English-Hitching derive theory and so on. Okay. back to saying something for the experts who like higher categories, the point of saying this was this lasagna algebra business is that I avoided the need to talk about four categories, which are big and scary things. But for people who like to try and think about four categories, I just want to say a lasagna algebra is a very particular kind of four category. It's one where there are no 0 and 1 morphisms, or well, there's just one of them. And the 2 and 3-dimensional stuff is just codimension 2 manifolds. And categorical language, you could say, sort of those are generated by a self-Killing 2 morphism. Okay. But the point is that rather than having to deal with all that language, we have this very concrete algebraic object that captures that. Okay. Knowing that this is related to a four category, though, ensures us that we can use some other ideas from the TQFT framework. And in particular, while this associated a vector space to a 4 manifold, there's also a natural way to associate a K category to a 4 minus K manifold, and there are nice gluing formulas when you decompose manifolds into pieces, and we'll be able to try and use those gluing formulas a little bit later. Okay, so now that we've talked about the framework, what do we need to do? We need to produce a lasagna algebra. And the next part of the talk is just going to be taking Khovanov homology and producing a lasagna algebra. So there are a couple of steps involved here. First of all, Khovanov homology, as it's usually defined, is something about knots and cobordisms in B3. And one of the first steps we're going to have to do is work our way up to S3 rather than B3. That's not going to be too bad, but there'll be a little bit of work. And then we're going to have to explain how to construct all these linear maps that a lasagna algebra expects. And we're going to have to get our hands dirty and prove some things about Khovanov homology, which we weren't previously known. Okay, so let's talk about this B3 versus S3 issue first. So here's the simple-minded version of what Khovanov homology is. It's defined combinatorially. So given a link diagram, it tells you how to associate a particular chain complex of graded vector spaces. Given a Reidemeister or Morse move, it gives you a chain map between those chain complexes. And given a moving move, that is a way of going from one presentation of a surface by a Reidemeister Morse moves to another presentation of that same surface, Khovanov homology constructs a homotopy between those chain maps. Now, you can then hit that whole business with taking homology, and well, for a link diagram, we get a doubly graded vector space, and for a Reidemeister or Morse move, we get a linear map. Those vector spaces. Okay. So the first step is just getting from link diagrams to honest links, but that's sort of an easy soft thing. This just uses the fact that if you look in the category of links in V3 with morphisms, cobordisms in V3 cross I, there's this nice subcategory, links that have a generic projection to the equator, along with cobordisms which have a generic projection. And I mean, that subcategory is what I defined Khovanov homology on, but it's an equivalence of categories. So you can just use that equivalence to lift Khovanov homology up. It's an honest invariant with actual embedded links in the three-ball. It gives you an actual vector space, and it gives you an actual map for an isotopic class of cobordisms. Okay. So fine. We're in B3 rather than working with diagrams. Now we need to work in S3 rather than B3. And again, this isn't so hard, but already we're going to run into a little obstacle at this point. So if you've got a link in S3, how can you use Khovanov homology to produce a vector space? Well, if you delete a point in S3, now you've got a link in something that looks like B3, so we can use Khovanov homology there. But we've made a choice, and we want to be sure that we don't break anything by making that choice. So to get around this, we're going to build this funny vector model. The base space is just going to be the complement of the link in S3. Okay? And over each point, what do we do? Well, we delete that point and think of the link in the complement, and we build a fiber of that point, which is just the usual Khovanov homology of that link in S3 minus that one. Okay? And now I'll describe a parallel transport in this vector bundle. If you give me a path in the base, there's a path in the complement of the link. We can think about the link cross I in, oh sorry, there's a typo there, in S3 cross I minus the graph of this path. Okay? This now looks like some surface in something that looks like V3 cross I, so it gives us Khovanov homology gives us a map between the two So I've built this vector bundle with a parallel transport, and we'll just define the Khovanov homology of a link in S3 as the flat sections of this bundle with parallel transport. Now, when we decide we're going to look at flat sections, we better ask, is there any monodromy? We can go around loops. And later, we'll give some conditions, some extra things that you can know about Khovanov homology to ensure the monodromy is trivial. But for now, we'll just proceed assuming that that's the case. So of course, since we've got this flat parallel transport, if you just take a section and evaluate it at any point, it's an isomorphism. We haven't done anything fancy here. We've just sort of chosen all points at once to delete, rather than making a choice about which points to delete. Oh, so there's a vector space for a link in S3. What about cobordisms for a surface in S3 plus I? Well, this actually contains most of the idea for constructing the lasagna algebra, so we should go through this. We've got this surface in S3 plus I, and the first thing we should do is choose a path gamma in S3 plus I that connects the inner and outer boundaries and avoids the surface sigma. Okay, we're in 4 space, so it's very easy to choose a path, a one-dimensional thing avoiding this two-dimensional surface. Okay. Again, we can look at the complement of this path, and that's something diffeomorphic to B3 plus I. And so we define the map associated to the surface in S3 plus I as follows. We start with a link in S3. We delete the initial point of the path. That gives us an isomorphism. Now we're just looking at the Khovanov homology of the link in the ball away from that point. Now we use the surface in the complement of that whole arc to get us an element of the Khovanov homology of the outer link in the sphere minus some point, and then we just go back to looking at the flat section through that point. Okay? We haven't done very much. But that's a definition of the linear map associated with cobordism in S3 plus I. We did make a choice here. We chose some path gamma, and we have to ask, was this definition actually independent of the choice of gamma? But we're going to kick that one down the road and answer that a little bit later. Let's just now pretend that we know this definition doesn't depend on the choice of gamma. Okay, so now we have a nice invariant of links and cobordisms in S3. To get a lasagna algebra, we just do, yeah. Was over the not complement for each point that wasn't on the link. Yeah, so when we're looking at when we're trying to see if there's monodromy, we're going to have to look at the little meridians around the knot, and we're going to check that there's a trivial monodromy. Okay, let's build the lasagna maps now. We've already defined the vector spaces that the lasagna algebra has. We now need the linear maps. Okay, so given some lasagna diagram like we had before, we need to choose a collection of arcs that avoid the surface sigma. And there's going to be one arc for each interior ball that connects some point on the interior ball to the sphere on the outside. And let's just zoom in and have a quick picture of that. So there's 2 arcs, gamma 1 and gamma 2, ending at some point x naught on the outer sphere. And the arcs should avoid sigma, but again, because we're in 4 space, there's plenty of room to avoid sigma. Okay. So what is the map associated with this lasagna diagram? It's essentially just the same as before. We start with a tensor product of the Khovanov homologies of all of the inner links. We delete the point in each of those inner spheres where the arc gamma arrives. That gives us the first map. So now we've got a tensor product of links in things that look like V3. Now we go from that tensor product of Khovanov homologies to the Khovanov homology of the disjoint union of all of those links. That's something, so we're using something about Khovanov homology there, that there is this map from the Khovanov homologies of individual links to a Khovanov homology of disjoint union, but that's easy and not very surprising. Now, what does our lasagna diagram minus these arcs look like? Well, it looks like a copy of B3 plus I. We've got some surface in B3 plus I with our inner links on the bottom surface, our outer link on the top surface. So we have a map associated with that cobordism. And then finally, we go back from this particular point in 1, 5 to the vector bundle to the flat section, and we've ended up with a map to the Khovanov homology of the link in the outer circle. Okay, and again we have the same problem. Is this map independent of the choice of the collection of arcs? Yeah. So now it's time to pay our debts and deal with the three problems that we left over from before. We needed to check that there was no monodromy. This one will be defined. We needed to check that the map for the cobordism S3 plus I depend on the choice of counter, and that the map for the Lazanda diagram depend on the choice of the arcs. And the point is that all of those things work out great, exactly if this is true. So here we've got a movie, so it's just some isotopy of a knot, and we're just asking that Khovanov homology always gives you the identity map for this isotopy, regardless of what T is. So here we've got some tangle with 2 points, and it's closed up on the right by a string, and all that we're doing in the course of this movie is passing the string around behind the tangle, and then back around in front to get back to where we started. So the thing to notice that might convince you that this is the thing we need to check is that in S3, this surface is actually isotopic to the identity. Okay, you can sort of inflate the arc that we're moving out through infinity to get back to the constant isotopy. But in B3 cross I, this really is something non-trivial. Okay, so I guess I haven't exactly said the details, but it turns out to be pretty easy to check with each of the things we needed to check, trivial monodromy and the 2 independent statements. Exactly come down to this question. When you move your arc gamma in one of these choices, sometimes you move it across a surface, and the surface in the complement changes by exactly insertion or deletion of one of these little moves. So this is something that might be true about Khovanov homology. This mapping Khovanov homology is always the identity, but we have to go and prove it. So it turns out it's been a little hard to prove, and we've been stuck on it for some time. Actually, we've not only been stuck on it, we've announced various false proofs of it, I think, over time. Not in print, fortunately. But it's a little surprising that this is hard to do. We have a version of Khovanov homology which is functorial on the nose, and it's sort of surprising that in that setting, we can't check that map. And what we've decided to settle for more recently is a proof in characteristic 2. So Khovanov homology, remember, gives you vector spaces for links. Now they're vector spaces over the field with 2 elements. And so I'll explain now the proof of this fact about Khovanov homology if you're willing to settle for working mode 2. So the nice thing that happens mode 2 is that there's an exact triangle for Khovanov homology, and the maps in this exact triangle are induced by the obvious cobordisms. So what do I mean here? So I've got the Khovanov homology of 3 different links here, which are related by resolving some crossing. And what I'm saying is that if you look at the homologies for these 3 links, there's a long exact sequence related. But the important thing is that the maps are actually induced by cobordisms. Going from each little link to the next one, there's an obvious saddle move that gets you from one to the next. Okay? Now, since the maps there are induced by cobordisms, this exact triangle is natural. That is, it commutes with cobordisms that are happening outside the ball that I've shown here. Okay? So what I want you to imagine is, I guess there'll be a picture of this in a moment, but a prism over this picture. So it's a triangular prism with the triangles on top and triangles on the bottom. Okay? Inside each triangle, we're doing these maps that modify the link inside the ball near this crossing. And the vertical maps are the maps induced by some cobordism which is constant inside this ball and does something else outside. Okay? Since Khovanov homology is functorial, certainly mod 2 it's functorial, all of the faces of this prism. Okay. So, yeah, I guess I can also explain what goes wrong with this when you don't work mod 2, but maybe I'll skip over that in my summary. So once you have this natural exact triangle, the proof of this theorem is really easy. You just induct on the number of crossings and use the 5 line. So what I've done here is drawn this prism I was talking about a moment ago, but on each vertical edge of the prism I've drawn 2 different maps, the identity and this sweep around move that moves a strand around the outside of the knot. And if by our inductive hypothesis the sweep move equals the identity on knots with lower numbers of crossings, the 5 line lets us conclude that for the knot that we're interested in. We then just have to do the base case, and it turns out the base case, this fact is really easy to prove for unlinks. It does use something about Khovanov homology. It uses the fact that if you take 2 unknots and pass one through the other, okay, so that's one of the generators of the loop rate loop, then that's actually the same, that gives you the same map as if you just move the 2 unlinks around each other. It doesn't keep track of unlinks studying through each other. And that fact lets you quite easily prove the base case for this interaction, that the sweep move is the identity for unlinked.
Is that the base fact true?
Yeah, and that the base case is true as equal. The only bit that doesn't work as E is the exact triangle is sort of broken. Okay, so that's the end of the proof. Oh, sorry. This last one? So, okay, so ignore the first 2. Look at these last 2. These last 2 pictures are meant to be the isotopy where you start with 2 unlinks and you pass one through the inside of the other. Okay? And what this is saying is it doesn't matter if you pass this one through the other guy, or this one through that one, or you just swap their positions and never come close. Okay? Khovanov homology, another way of saying this is that Khovanov homology gives you the trivial representation of the motion group of unlinks. And in fact, well, maybe I should even say the proof of all of these equalities here is just there's a neck-cutting relation in Khovanov homology, which essentially lets you slice apart one of these cylinders at a sum of terms that the top and bottom of the cylinders aren't actually connected, and then you can just reconnect them back up without passing through the other circle. Yeah. I mean, it's, maybe let me just quickly, okay. So back here, the problem with the version of Khovanov homology that's functorial over Z is that there is this long exact sequence for Khovanov homology there, but one of the corners, this bottom left corner, isn't actually the Khovanov homology of a link. The problem is just that if you imagine some orientations on that top guy, there's no way of consistently orienting both of the, so imagine the top guy's oriented upwards, both strands are oriented up the page. Then you can't consistently orient the bottom left one. So that's fine. I mean, we have some complex that goes there that makes this an exact triangle, but the bottom left corner isn't the Khovanov homology of a link. Now, we've got various ideas about extending Khovanov homology to links that have some disorientations on them, and if we can prove functoriality for those, now we've got to think about surfaces with disorientations on them as well, then we can make this exact, this triangle natural, but for now, we don't know. Okay, so I actually wanted to, where are we? Okay, yeah, so we've looked at Khovanov homology, we've checked this extra fact about Khovanov homology, at least one, two, we didn't know before, and we've learned that this extra fact gives us a lasagna algebra from Khovanov homology. And so in particular, it gives us a vector space value invariant of 4 manifolds, following the recipe that I have under. But certainly what I should do next is try and tell you something about what this invariant is and what the prospects for calculating it are. But I thought instead that I would imitate some of the speakers at Mike's other birthday conference. Maybe not all of you know, but well, I mean, all of you know that Mike is a famous physicist now. But he had another birthday conference about a month ago, 2 months ago, down in Santa Barbara, where all the physicists came along instead of the mathematicians. And the thing that really struck me listening to all of their talks, well, one, they were very enthusiastic about Mike's contributions in condensed matter physics, but secondly, that apparently Mike had tried to kill each and every one of them by taking them climbing somewhere. And all of them had a story about the time that Mike tried to kill them. And so I thought that I should try and include such a story as well. But I realized that actually, on the climbing trips that I've been on with Mike, on the climbing trips I've been on with Mike, I don't think he's ever actually tried to kill me. We've been to some pretty exciting and beautiful places on a few applied knot theory courses over the last couple of years. But most of them have been fairly sensible. And the only time that Mike has tried to kill me was actually when we were kayaking. And so this was in New Zealand, in a nice place called Hahe. We were there after a conference in Wellington about 4 years ago. And this photo was actually very deceptive. Most of the time we were there were huge waves, and it was raining, and it was great, because there were no other people out there kayaking. And once you got past the big waves and back into the sea caves, there was no one else there to ruin the experience. But 1 or 2 days there was sunny weather, so got a photo there. But while we were kayaking around the coastline here, at some point Mike pointed out this sea stack sitting out in the middle of the bay, and suggested we paddle out and have a look at it. And when we got there, I could see from the gleam in his eye that he really wanted to climb it. And so we started kayaking around the base of it. And as you can see, the left-hand side is overhanging. You come straight out of the water. There was not much prospect there. And the right-hand side was a little bit better. But there was clearly no prospect of pulling up our kayaks on dry land or anything if we got out. I mean, you could maybe get onto the rocks, but there was no place to put a kayak. So I assumed that we were done and we would paddle off somewhere else and continue looking at sea caves. When Mike suggested that actually what we should do is one of us should stay sitting in their kayak, and the other person would jump out of their kayak into the water, and then swim up to close to the rock, and tread water until a big wave came. And when a big wave came, we would grab hold of the rock, and keep holding on to it as the water receded, and then very quickly climb up out of the way before the next wave came. And this sounded kind of exciting, so we had to give it a go. And I got a few photos of Mike on his way up. So this is, I mean, it was all too exciting to take photos while Mike was actually swimming amongst the waves, but he's actually safely clambered across and is clinging onto the rock up there. Yeah, he's a little yellow blob. That's his life jacket. We didn't have ropes or helmets, so we decided life jackets to do the safety equipment. And here's another one as he proceeds a little bit further along the rock. And some more. He still hasn't got very high, and you can see there's quite a lot of rock above him, but after a little bit of effort, he started getting up. And then this is my favorite photo. I'm not sure that you can actually see where Mike is in this photo, but I hope you can see that it's a fairly steep cliff, descending straight into the water, and it's sort of covered in dirt and vegetation and moss and so on. But Mike is in this photo. He's that tiny little yellow dot there. That's his life jacket climbing up through the trees. Quite a long way above the water at this point. But it all sort of went to plan, and Mike went up and came back down, and jumped back in the water and swam back to his kayak. And so, of course, then I had to have my go as well. And I guess I took the camera with me, because there were no photos that proved that I actually did the silly thing. But I followed mine. And yeah, so eventually all was well, and we didn't actually die. But it did take, oh, sorry, I think I pressed the wrong button, sorry. It did take at least 15 or 20 minutes of recovery before we were ready to start talking about mathematics again. Okay, so that's enough about climbing. So what are the prospects for doing calculations for this gadget? Well, yeah.
What was the quality of the rock?
What you might expect for a sea stack with lots of plants growing out of it. It was kind of the consistency of sort of calcified bird poo. The plants fell out. There's another photo that I was thinking of putting in, which is actually from a different pile of rock that we climbed out in the middle of the ocean on this trip. It's sort of hard to interpret the photo, but Mike is actually burrowing through the dirt underneath the roots of this big tree that's growing right on the edge of the cliff, and we couldn't get up through it, so we decided we had to go underneath this plant. Okay, calculations. Well, there's two main prospects, I think, to calculating this thing. First of all, actually, I guess I didn't put this on a slide, maybe I should have said it. That we know for a link in the boundary of V4 that we just get the usual command. It's obvious that this thing I've defined just gives some quotient of the usual command, because you can take any picture in V4 and just envelop up all of the quantities, okay, in a big ball. Okay? So certainly, whatever this vector space is, it's spanned by the usual command. But you might think that there are more relations that you only see when you go down to some smaller number of balls and recombine them in some other way. But you can show by a pretty easy argument just that there's a pairing between the Khovanov homology of a link and its mirror image that lets you see that it's not a deeper quotient. So the 4 ball, we've just defined the usual command. So happily, that's actually something finite dimensional, which maybe is a good sign that we've got something. But I don't think we expect it to be finite dimensional anywhere else. So there are two main prospects to actually calculating this thing. And the first of them is by using gluing formulas. Whenever you have that TQFT set up, there's a recipe that says, well, you can calculate the invariant of some manifold by chopping it into pieces, calculating some algebraic invariance of the pieces, and then assembling those together by the right algebraic operations. So I wanted to say what that sounds like in this setup. So first of all, we've defined vector spaces for 4 manifolds. Let's define 1 categories, in fact, star 1 categories for 3 manifolds. So given a 3 manifold, if it's got boundary, you get to choose a finite subset of the boundary. It's not so important. We can define a category for this 3 manifold whose objects are tangles in M. If there's boundary, the tangles should meet the boundary in exactly that subset C. And the morphisms between 2 tangles, well, what do? You've got 2 tangles in M that lets you build a link in M cross I, is some 4 manifold, okay? And this recipe associates some vector space with that 4 manifold with the link in the boundary, okay? So we declare that vector space to be the homospace between 2 tangles. And it's pretty easy to see that there's a composition. Basically, if you have a labeled lasagna diagram in one M cross I, another labeled lasagna diagram in another M cross I, you can stick them together in the right direction. You get a new labeled lasagna diagram. That's exactly the composition. Okay. Now, if your 3 manifold was a part of the boundary of a 4 manifold, maybe it's connected component, maybe it's just a codification 0 subset of the boundary of a 4 manifold, then we can build a module over this category that I just mentioned. So the 4 manifold with M in its boundary gives a module over the category associated with M. So what is a module over a category? Well, for each object in the category, I need to tell you a vector space, and then for each morphism in the category, I need to give you a map between the appropriate vector spaces. So what do we do here? Well, for each tangle in M, oh, sorry, I should say one more thing. Let's, through here, fix some tangle in the rest of the boundary of W4. So the boundary of W4 consists of M and some other stuff, and there's a fixed tangle in the other stuff. So given a tangle in M, I need to tell you a vector space. What is that? Well, you just take A of the 4 manifold with the 2 tangles in the boundary, and it's easy to see that this forms a module over the category associated to M. That's just saying if you have a labeled lasagna diagram in W, you see M sitting on the boundary somewhere, you can paste on a lasagna diagram, a labeled lasagna diagram in M cross I, and then use a little Kohler isotopy to get back to W, and that's giving you a map from, well, it's given an element of the vector space of W and a morphism in this category gives you a new vector in this vector space of that. Okay, so 4 manifold, 3 manifolds in the boundary in modules. So if you've got a 4 manifold with 2 copies of M in the boundary, then the invariant of that 4 manifold forms a bimodule over the category associated to M. And the general nonsense of TQFTs tells us that we can compute the vector space associated to W glued to itself along M as the self-tensor product of this bimodule A of W over the category A of M. And an example of the sort of thing that you want to apply this to is you can think of B3 cross S1 as just a single four-ball glued to itself along a B3. So suppose we wanted to compute the invariant for B3 cross S1 where L wraps around the S1 copy twice. Maybe it's just two original loops, maybe it's got a crossing in it, something like that. What do? Well, we slice open W along some B3. And so what do we see there? We see a B3 with two marked points in the boundary where the link had originally passed over. And so we need to understand this category associated with B3 with 2 points in the boundary very well. And in this particular case, with just 2 points, we think we know what that category looks like, and we think we know how to plug it back into this tensor product formula. And so we have sort of some tentative answers for invariance for B3 cross S1, some very simple things in the boundary. But I'd say that those are calculations at an engineering level of rigor, not even a physics level of rigor. Sorry if there are engineers in the audience. Okay, so that's one approach, using gluing formulas to compute these invariants. Then the other one is actually, in some sense, an advertisement for what Kevin and I have been doing with the blob complex. Khovanov homology is usually calculated recursively via this exact triangle that I talked about earlier. Okay? You don't actually use the definition in practice. You just take your link and resolve some crossing and calculate the invariance of the two simple links, and then use the long exact sequence to recover the Khovanov homology of the original bigger link. But the long exact sequence just doesn't work anymore when W isn't B4. We could hope that it works. I mean, we can think about the invariant for a fixed form manifold with 3 different links in the boundary that differ by a resolution of the crossing. But at least our engineering level calculations in B3 cross S1 suggest that the long exact sequence fails. And this is unsurprising. And we're constructing A by taking some big quotient, and there's no particular reason to expect exactness to survive. So the point of the advertisement is that the blob complex allows us to define a chain complex, A dot, of the pair form manifold with a link, such that the zeroth homology of this chain complex is the thing that I've been talking about for all of today. Now, the long exact sequence for Khovanov homology does actually continues to hold for this chain complex. Okay? And so that means you can think about that a little while, and you can get some spectral sequence that you know converges to zero. And so the hope now is that if you want to compute, even if you just want to compute the bit I've been talking about today, A of W comma L, maybe what you should do is calculate the whole blob complex for the 2 resolutions of that link after you've chosen a crossing, and then put all of that data together, those whole chain complexes, use all of that to recover the chain complex, or maybe just H0 of it, for the original engineering. And this idea of a variation of the definition of TQ of T that preserves exactness was exactly the motivation for Kevin to first start thinking about the blob complex. So in fact, this is actually the motivation, even though historically maybe they're going to appear in print or like that.
A while back, I thought you were telling us that the long exact sequence of these 2 integer coefficients failed even in these 2, and that's the reason for you need to see 2 coefficients.
Yeah, so we can't show that I mean, even in the 3 sphere, you can use the long exact sequence to do computations.
Well, also it's a question of homomorphisms rather than the vector space.
Yeah, the critical part there is checking that the exact sequence that you write down actually commutes with cohorts, so that we can do these sort of induction proofs. It still lets you do computations. Yeah, so I'm still sort of in this slide implicitly still talking about mod 2 where we can actually make things work. Okay, those 3 slides of computations maybe weren't very satisfactory, but that's what we have at the moment. And hopefully maybe more